Welcome back to Computer Lessons.
In our previous episodes, we examined the brain, which is the CPU, and the memory, which is the RAM. But if you were to buy these incredibly expensive components and simply place them on your desk, absolutely nothing would happen. They are isolated geniuses without a home. They need a communication network and a common ground to exist. Enter the motherboard. To the untrained eye, it looks like a confusing plate of plastic covered in sharp metal spikes. But look closer. It is actually a futuristic city viewed from above. It is the infrastructure, the nervous system, and the backbone of your entire machine. Today, we are not just going to learn what it does. We are going to learn the physics of how it works. Have you ever stopped to wonder why we call it a motherboard? It is a term that comes from the very early days of computing history. Before modern integration, computers used something called a backplane, which was just a connector with no intelligence. Every function, including the CPU and memory, was on a separate card that plugged into this backplane. As technology evolved, the main board began to take on more responsibility. It became the mother to all the other circuit boards, like sound cards and network cards. These smaller cards were historically called daughter boards. So, the motherboard is the parent that holds the entire digital family together. Let's start with the board itself, which is not just a piece of plastic. It is a complex technological sandwich known as the PCB, or printed circuit board. Modern high-end motherboards have 6, 8, or even 10 layers stacked on top of each other. The base material is usually fiberglass, which acts as an electrical insulator. Sandwiched between these fiberglass sheets are extremely thin layers of conductive copper. And what about that color? Whether it is green, black, or white, that is just a coating called the solder mask. Its job is to protect the copper traces from oxidizing and to prevent solder from bridging between two points that shouldn't connect. Now look at the surface of the board. See those thousands of tiny lines running everywhere? Those are called traces, and they are the wires of our digital city. If you look closely near the CPU and RAM, you will notice something strange. Some of these traces are not straight. They wiggle back and forth in a zigzag pattern. This is not for decoration. This is physics. Electricity travels extremely fast, but its speed is finite. The CPU operates at billions of cycles per second, meaning timing is everything. If one trace is shorter than another, the electrical signal will arrive too early. If a trace is longer, the signal arrives too late. To prevent this data crash, engineers force the electricity on the shorter paths to take a detour. By wiggling the line, they make the path physically longer. This ensures that every single bit of data arrives at the exact same nanosecond. This is called trace length matching. Before you build a PC, you must choose your size. Motherboards come in standardized dimensions called form factors. The most common standard is ATX. It is large, offers the most expandability, and fits in standard towers. Then we have Micro-ATX, which is a square board, shorter than ATX, and usually more affordable. For the enthusiasts who want a computer the size of a shoebox, there is Mini-ITX. And for the extreme workstation users, there is EATX, or Extended ATX, which is massive. Despite the size difference, they all perform the same core function. But remember, a giant EATX board will physically not fit inside a small case. Always check your compatibility before buying. The most critical real estate on the motherboard is the CPU socket. Think of this as the throne room. This is where the physical connection between the brain and the body happens. There are two main types of sockets. LGA, or Land Grid Array, has the pins on the motherboard itself and is used by Intel and modern AMD chips. The older style PGA had the pins on the CPU. These pins are incredibly delicate. If you bend even one of them, your computer might never turn on again. The socket uses a mechanism called ZIF, or Zero Insertion Force. You drop the CPU in gently and then use a lever to clamp it down, ensuring perfect contact without using force. Surrounding the CPU socket, you will see a cluster of blocky components and capacitors. These are the VRMs, or Voltage Regulator Modules. This is one of the most important, yet overlooked parts of a motherboard. Here is the problem. Your power supply sends 12 volts of raw electricity to the board, but if you fed 12 volts to a modern CPU, it would instantly fry. The CPU needs a very specific, very low voltage, usually around 1.2 or 1.3 volts. The VRMs are the power plant that steps down this voltage. They also clean the electricity, removing noise and ripples. On high-end motherboards, you will see massive metal heat sinks covering the VRMs. This is because converting voltage generates heat. If the VRMs get too hot, they will throttle your CPU to save themselves, slowing down your computer. Further down the board, usually covered by a flat heatsink, lives the chipset. While the CPU is the king, the chipset is the prime minister. In the old days, we had two chips, the North Bridge and the South Bridge. The North Bridge handled high-speed tasks like memory, while the South Bridge handled slower things like USB. Today, the North Bridge is integrated directly into the CPU for speed. The chipset we see on the board now is essentially the South Bridge. It acts as a traffic cop for your USB ports, your hard drives, and your sound card. It collects all this data and sends it to the CPU over a narrow link. This is why motherboard tiers matter. A better chipset, like a Z series or X series, allows for more connections and higher speeds. Next to the socket, we have the DIMM slots for your RAM. You will notice there are usually 4 slots, often color-coded in pairs. This is to guide you in using dual-channel architecture. RAM talks to the CPU over a 64-bit wide path. Ideally, we want to double that width to increase speed. By installing 2 sticks of RAM in the correct alternating slots, the motherboard opens a second lane. This effectively creates a 128-bit wide highway for data. If you put your RAM in the wrong slots, you are forcing high-speed traffic into a single lane, creating a bottleneck. Look at the bottom left corner of the board. You might see a translucent yellow line running through the PCB. This is the audio isolation path. The rest of the motherboard is noisy with electrical signals. To prevent a buzzing sound in your headphones, engineers physically separate the audio section from the rest of the board. They essentially cut the PCB layers to create a moat around the audio chip. Then we have the PCIe slots, which are the expansion highways. The top slot usually has 16 physical lanes connected directly to the CPU. This provides massive bandwidth for your graphics card. Finally, on the back, we have the rear I/O. This is your bridge to the outside world, hosting USB ports, Ethernet jacks, and display outputs. One final tiny detail. See that silver coin battery? That is the CMOS battery. Even when you unplug your PC, this battery keeps a tiny volatile memory chip alive. This chip stores your BIOS settings and the system time. If your computer ever fails to boot, look at the debug LEDs on the side. These tiny lights will tell you exactly which part, CPU, RAM, or GPU, is causing the problem. So the motherboard is more than just a holder. It is a marvel of electrical engineering that coordinates the chaos of billions of signals. Now that the city is built, we are ready for the artist. In the next video, we will focus on the component that gamers dream about, the graphics card.
If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.